Siman-Tov. Shalev doesn't really need an introduction in this forum, as he was a student in this department. He worked with Einat and interacted with many other people. Shalev is currently a postdoc with Emily Brodsky in University of California in Santa Cruz. And although he's there, he's actually physically here and is available to talk with people in the building. Today he'll talk about shearing in the presence of water, observations on glacially polished surfaces, and granular flow experiments.
Thank you. Good morning. Thank you very much. So today, indeed, I will talk about shearing in the presence of water. I will concentrate on two parts of my projects there. One is observation on glacially polished surfaces, and these type of surfaces, and the other, the granular flow experiments that we run in our lab there. I did this postdoc at UC Santa Cruz with this symbol of banana slugs. We have the slugs there. And I want first to thank all the people that helped me there, especially the people in the department, the different people in the department, especially when I interact about glacial polish project. And I used to be in the seismology group there, and really the amazing people that I found there, and especially my mentor, Emily Brodsky. A best friend now and a great mentor. So this is what I will talk about today, and why to talk about shearing in the presence of water. So because they are there. They are in shear zones, in many shear zones in the world. One example is landslides. Change in water table levels in landslide can trigger landslide. They can become the stable slip or no slip on landslide detachments to something which can make a big hazard and destruction. The other thing is glaciers. At the base of the glacier, there is water, the meltwater, and if we want to know what is the mechanism of glacier slip, we would like to know what's going on there with the water, and lastly, earthquakes. At some point, we know from structure, we know from other observation, the water exists and they could be important, very important in earthquakes. So that's what we want to study. However, despite all this that we know that there exist, most of the experimental, especially the experimental studies and in general studies, concentrate with dry material. And the reason why, because usually it's just easier, especially in experiments, it's easier to perform, and also it's less complicated. So if we want to understand shear, we will start with the dry, and after we will move to the saturated experiments. So today I will talk about naturally polishing at the base of glacier, which mostly should affect our understanding maybe of glaciers. However, it also may reflect on our understanding of earthquakes and landslides in general. The effect of water that I will show in shear granular flows, it's more a physical problem, basic physical problem, that actually can affect everything, or the global understanding of these physical processes. However, more study will be required for it. So I will start with the coating layer we found on glacial polish. So this is a glacial polish from Yosemite National Park. You see the shiny surfaces with some lineations on it. This work was done with Greg Stock. He's the geologist of Yosemite. Emily Brodsky, of course, and Joe White from the University of New Brunswick, Canada. He's an expert. He's a structural geologist and expert with transmission electron microscopy. So why? Why to study, and especially during this talk, we'll concentrate on why to study, the implication, and I will shortly touch the results we have. So one of the things when I end with my PhD, many questions remain unanswered. By the way, what I did is studying polished surfaces in false environments. So one of the remaining questions is about where we find in which rock types we find glacial fault mirrors. So we can find them in chert, like the nice example from San Francisco, the Corona Height Fault, in Kvargila D, in limestones, in Eocene limestone, dolostones near El Mukek, in the Lac region, in rhyolites. However, in granites, I never see mirror-like surfaces. And when I asked structural geologists around the world, the answer was maybe there, maybe not. But although we find faults in granites, we don't find the mirror-like surfaces. And the question is why? We do find them in the countertop in our kitchen, like the example here. And moreover, we find them in glacial polish. So they can polish, not they are just that they exist, they even preserve better on granite in the post-glaciated environments like in glacial polish. So why? The other is maybe better understanding glaciated glaciers and mechanics of glaciers. And this is a simple illustration of how a glacier looks like in Yosemite, more or less. So there is the bedrock. In most of Yosemite, we are talking about granodiorites. And then on top of it is the glaciers. At the base of the glacier, we have usually a layer of till. In Yosemite, it's less than 10 meters. And the thickness of the ice above it, the dirt ice with fragments, of course, and some dust, is about 1,000 meters. The amount, actually, what we get from this mass is normal stress of about less than 10 megapascal. That is lying on this granodiorite surface. And what we know about slip and the localization of slip in glacier, these are two main strain accumulation. One is that the slips appearing on this surface between the glacier and the granodiorite and make the striation and other things that I will show you later. And the different strain accumulation is by plastic deformation of the glacier itself. So this is how a glacier in general looks like in the alpine environments. And we are interesting to understand what is the structure here that may tell us maybe about ice quakes. Ice quake is earthquakes at the base of a glacier. More and more research is done and compare between earthquakes and ice quakes. So maybe can we understand something from the structure below about these erosion rates? Can we understand something from glacial polish on erosion rates? What is the glacier history in Yosemite and in general? Can we use this glacial polish to study it? And glacier mechanics. If we know how it's formed, maybe we can tell how a glacier is moving. So we have no real conclusion about all these topics, but I think we started to build an interesting insights about this issue. That's, by the way, how a glacier looks like today. At the base of the glacier ice cave in Yosemite National Park. What we don't see here is the T layer. So this is the glacier with a lot of dust and some big fragments that make the striation. Here, Marcy point on a fragment that's detached from the sail here. And again, something that can make a striation there. And the other point is evolution of landscapes. And I'm talking especially on chemical weathering. Here we see an example, again from Yosemite, of apelite dikes. And what we see is that the polish is preserved better along the dikes, while it's weathered around it. And sometimes it's actually preserved better on big crystals, on phenocrysts in the granodiorite. So what I want to take from here is that if we have shiny surfaces, and that's my definition to glacial polish, it's optically smooth. That's the reason it's shiny. If it's optically smooth, the meaning usually is that there is zero weathering. Zero weathering for thousands of years. And I will show you an example of about 14,000 years of exposure, and it remains polished. So The question is why, and another observation we have is weathering pits. Weathering pits are circular holes. It's in the middle, they are weathered. It's the original granular after the polish exposed, and around is the shiny surface. You can see it here in a larger scale. And I also will pass now an example of this kind of pits. Around it's polish, in the middle is the original apelite. By the way, it's an apelite diac, an example. And we are not the first to observe all these observations of glacial polish. For example, Joseph Laconte, he's the first geologist at UC Berkeley. In the 1870s, he visited Yosemite National Park, and this is part of his notes. And he mentioned that it's remained as fresh as the day they were left by the glacier. And this is kind of an assumption to what we are doing in this work. If ever the polished surface scales off, then the disintegration proceeds as usual. And this is true for example, these weathering pits. After it scales off, the polish, we are getting the regular pattern of weathering in this environment, in granodiorite environments. And lastly, as a good geologist, he's talking about debate he has, and debates about how it's so resistant to weathering. So Whitney thinks that the polished surface is hardened by pressure of the glacier. I cannot think so. The smoothing, I think, prevents the retention of water and thus prevents the eroding. And today I will try to contribute to this debate by our new observations. So what we know till now about glacial polish, that it's a material removal process. And if we're opening textbooks of glaciers, we'll find inside this polish is smoothing of a rock surface resulting from the removal of small asperities by overriding rock particles and ice. And indeed, when we are looking at the large scale, at the field scales, we do see crescentic shaped marks, chatter marks, these marks here, and surface striations, similar to what we see in faults. All these are marks usually for brittle, known as brittle deformation, and it supports the material removal. However, can we think that maybe there is additional process? Not the only process, but an additional process there. And from my PhD work on the same type of surfaces that we find in faults, not in glaciers environments, we see striations, we see the same shiny surfaces, chatter marks, etc. However, when we look at the small scales, we see that the polished surface is actually formed by a coating layer of micron-sized thick layer that's is on top of the surface. It's made of amorphous material and nanoparticles, and it's formed during sleep, during fall sleep. And the question if it's the same to any polish. If, for example, we are taking a sample, manually polished sample, and a glacial polish, both will show a coating layer, and that's the reason they are shiny. And I will move two samples. One is just another sample of glacial polish for Yosemite. One side is the regular detached bedrock, and the other side is the polish. You can see the striations there. The other sample is exactly the sample, part of the sample I'm showing here. One side is the manually polished with diamond heads, and the other one is the glacial polish. I can compare. And by the way, you can guess already from this image the answer. Here there is a different color for the glacial polish. Here is more transparent, and we can see the original crystals. So the answer is yes, we can get manual polish. We can get a polish just by removal of material and having a very smooth topography. However, in glacial polish, we do observe a coating layer, a significant coating layer, between micron to a few microns. So today I will concentrate on this coating layer, explain and what we can learn from it. So what we did is going to Yosemite National Park and collect and recorded glacial polish from the upper mountains, Mount Lyell, in Yosemite, in the active glaciers, the blue parts here, down the Lyell Canyon that was shaped by the glaciers, and the last glacial maximum, and Tuolumne Meadows, and the domes around it. The dome is a big piece of rock that's shaped by the glacier slip. So more about what I will talk about, you can find in our paper that's published months ago in geology. So the first sample I will talk is the ice cave in McClure Glacier. It's the last active glacier in Yosemite. Has about tens of meters thickness, and it's the bedrock there is metavolcanic rock. Here the arrow should show some people. If you see, this is the entrance for the cave. So these are a few hundred meters of glacier. This is from inside the cave. The shiny surfaces here are ice and not the rock. This is the sail. This is the floor. And we are talking about this location. I collected the sample, about a few centimeters, 1 centimeter size sample, and then I go to the lab, happy to resource, and using focused ion beam, I cut samples that are similar to slides that we are using in cross-section in optical microscope. However, they are much smaller. So the size is about 10 to 15 micron, the thickness is about 100 nanometers. And then we are looking at with transmission electron microscopy. So this is a bright field image, which means that the voids are in white, lighter colors. And this is an amphibole crystal of the original bedrock. The green line is the polished surface, is the outer, this is inner. And what we can see easily is that the amphibole crystal is very intact, besides some cleavage planes that cross it. And above the red line that I marked here, there is change. There is much more deformation in the amphibole crystal, and also there is a bend toward the ice sliding direction. So something like this. And let's take a look in zooming in into it. So these are the cleavage planes, and they are bent toward the surface. Okay. The original structure of the lattice still exists by X-ray diffraction. We can see it's still the same amphibole, but rotated. And another important observation is that following these arrows, that there is a reduction of grain size toward the surface. So a real observation of formation of nanoparticles just by this mechanism of crushing and having denser joints, denser fractures in the rock. So we have the material to form a coating layer. Now we see the starting of having this coating layer here in the margin of this cross-section between the yellow line and the green line. It's a kind of breccia. And zooming in, we can see that's the amphibole particle that came probably from here, smeared and get into this piece, fill it, making the surface smoother, less topography. But we can also find some other stuff that came, these particles that came from a little bit or more than a little bit farther from this place. By the way, all these are coated by a thin layer, tens of nanometer amorphous material coating that make this material, this breccia, to remain in the same place. And not to escape while I'm washing the sample before, when I'm preparing it, and etc. The other sample I want to show is on granodiorite sample from Duff Dome. It's about 20 kilometers from the upper mountains, from the glaciers. Exposed about 14,000 years ago. This is the sample I will talk about. Again, it's a weathering pit. And we get a coating layer now, a continuous coating layer. We see an inner layer of amorphous silica. Here is the amorphous structure, no structure, this is amorphous with X-ray diffraction in TM, and an outer layer of phyllosilicates with many fragments inside. Now, the bottom is a plagioclase crystal of the original bedrock, of the granodiorite, and the fragments are different. They have quartz, feldspar, plagioclase, and they represent a mixture of the granodiorite, of the original granodiorite. Now, what is the mechanism of formation of these layers? We're not sure about it, but we suggest, it was suggested first that it's precipitation from the subglacial water. there is a thin layer of water there that is moving and just precipitate material. That was published and suggested by Bernard Halley in the 70s. And it's a possible explanation. What we suggest is also a combination with smearing of the material and adhering it to the surface. And we suggest it because especially because one of the observations, which is this cluster of fragments, that it seems that a beer particle broke, and then it's smeared with the glacial sliding direction, but it's preserved at the same location. So we can see the tail of the small particles. So it's right for the iron oxide here, for the K feldspar, and to the plagioclase. And that will happen if the material is viscous, is more like a mud material. So we suggest a cataclasite flow formation, similar to what's happening in faults. Okay, so the take-home messages from the results is that we have micrometer size coating layer that is observed on top of the glacial polish, and that the coating is possibly formed during glacial sleep. What is the next steps we are taking there? In terms of weathering, chemical weathering, we are trying to understand why it's resistant and what we can learn from it. So what's happening is actually reducing the porosity. This layer, the brown layer, is the coating. It's reducing the porosity and permeability, and therefore less water can get into the original crystal. The chemical compound, the material is actually the same over the surface, and there is not a differential weathering of different minerals. And the surface, as was suggested in the same code that I showed before, is smoother, and therefore water can flow faster on the surface. However, when there is a break and there is a hole there, and water can enter into it and start the weathering process, what we get in larger scale is lateral evolution and weathering of this bit, and we get these bits. A nice comparison with what Ron Goldberg did in his master with Simon and Emmanuel is an experiment with AFM. So it's totally different scales from the glacial polish. This is 1 micron here. And he started with a polished surface from a dolomite fault mirror and a manually polished of the same dolomite fragment. And then he exposed it to water flow, and scan it under atomic force microscopy, and look at the evolution of the topography. And what we see, this is with time, the initial smooth surfaces are becoming something like karst weathering in the Z direction, and differently for the naturally polished, we're starting to get weathering pits that's actually evolved laterally. And also we are getting a sharp margin, very similar to what we see in glacial polish. And if the glacial polish scale off, we can get similar structures like in irregular polish. So that's one direction. The other direction is taking this coating layer and to date it and to say something about the evolution of glaciers in time and erosion rates there. So the first steps we did is a collaboration with Terry Blackburn from UC Santa Cruz and Nat Coble from Stanford. So first we look with laser ablation about the chemistry of these surfaces, in addition to what we did with the TDM. And we observe the same structure we observe in the TEMs. We can see in the chemical composition changing in the iron composition, so maybe it's reflect the phyllosilicate layer and some concentration of iron oxide in this layer, and then in the rock fragments there is increase of the iron. However, what is important is we are getting more uranium in the inner layer here, in the amorphous layer inside here, and that may allow us to use uranium thorium method in order to date it. So we tried with the SIMS, with the secondary ion mass spectrometer in Stanford, and what we get is an age of 34,000 plus minus 10. For me it was a huge error. It was hard to believe, but what was important, it's out of equilibrium, and while the rocks are about 90 million years ago, they formed 90 million years ago, this is giving a totally and measurable, and we can give an age of this part. So this is what we measure. And now what we are going to do next is trying to see if there is any chronology that we can suggest that we are taking in older surfaces and we can really see older dates. So what we are going to do is is going to moraines and trying to sample erratic boulders. Boulders that actually also get some polish in them. And this is an example from here. Michal gave it to me from the collection. So you can see a kind of erratic pebble. So I took my son, we climbed moraines and collected some samples. And what we want to see is the difference between an old moraine that was cut by a young moraine and see if the polish can date it. So this is another direction. And the last thing that will move us to the other part of the talk is the formation of glacial polish under lab conditions. And that's what I did in our lab, in the rheometer lab. So this is a rheometer that's supposed to measure fluid viscosity. However, we are using it to other things of, like here is kind of rock shear experiment and granular materials. And I glued a slab of granite from Duff Dome to the upper part, put a static slab at the bottom, glue a glass jacket, put inside a crash material from the same granodiorite, stress it, and then adding water, run it for 72 hours, which is about 25 meters or more, depending on the experiments. Normal stress of about 70 kilopascal, very low normal stress, about 7 meters of ice. And the glacial slip velocity, which is usually below 100 micron per second, and that's exactly the velocity I run here. And what we get after we open the surface is obviously a polished patch. So it's just a start. We are going to make some cross-section, see if the structure is the same as we see in nature, if what we suggest is the same, and also see by our rheology measurements what we can get about the mechanics of faults and the connection to the evolution of these surfaces, if it reflects something about the evolution of friction, and etc. So that's bringing me to the other topic of this talk, which is shearing of dry versus saturate granular materials. So this is our lab. This is the rheometer that I was talking about. Some other parts that are, now it's a little bit even fancier. You see the acoustic emission sensor here and the cell of shearing. We'll touch it later. But what we want to study here. Now, there are many works about granular materials. Now, when I'm sitting and trying to write everything down, there is a bunch, especially in physics, of experiments with glass beads and other stuff. However, there is less material with natural granular material. But what we use in the lab is beach sand and other minerals and see the difference between the things. So I think that's the important, our importance in the lab. So what we know is that in basically granular material strongly depends on the way they are shearing. And by that I mean that they can shear like a solid. It's a solid-like regime where most of the stress that is applied on the granular material is held by stress chains that are marked here by these lines. Differently, at higher velocities, and we'll talk about it immediately, there is gas-like behavior of the granular material. When they're actually having a lot of impacts in between them, they are moving very fast, and they look sometimes like ideal gas. So the way we know how our granular system is shearing, what's the physics there, is by something, an inertial number, a non-dimensional number, that is controlled by the grain diameter, by the density of the particles, the stress that is applied, enormous, because the confining pressure there. However, I will concentrate on the shear strain rate which is dependent on the velocity and the thickness of the system. So the shearing velocity of the upper wall in our system, and the reason I'm talking about it, especially about the velocity, is because that's the main parameter I control in my experiments. So looking at the results about what we know about the different regime, this is the dilation, how it's moving up and down, and the system, and this is the normal stress on the system versus the shear rate. And for very low velocity, what we get, and the very low inertial numbers, lower than 10 to the minus 3, we're getting the quasi-static regime, where when we are moving between velocities, there is no change in the dilation. It's still the same volume of the material. However, when we are getting to the inertial, grain inertial regime, we are getting dilation or increasing of stress on the particles. So these are the different regimes, and these are the numbers of where it exists. So in general, what you need to take, that's low velocities are low inertial numbers, and it will give frictional sliding, versus high velocities and high inertial numbers, we get collisional regimes. But the question is what's happened when we are going to add water to the system. And that's what I will talk about, this comparison between dry and water-saturated experiments. And again, I'm bringing it back to the reason we want to study, because we're interested in shear zones with water, earthquakes, faults, glaciers, and especially landslides. And within landslides, we have one type, which is the breeze flows, that also exists with a lot of granular material with different sizes. It's a slurry, there is a lot of also tiny material, maybe different viscosities, and all this, I think, can be contributed by our study about granular materials. So the system looks like this, and I will pass an example of the rotor we are using. So this is the moving rotor on top. We are shearing beach sand in the size of 300 to 417 microns. It's beach sand from Santa Cruz. We just collected there. We are gluing the beach sand to the top, to the rotor, as you will see in the sample that I'm passing here, in order to move the formation toward, into the grains, and not just on the boundary between the steel rotor and the grains. We have a ring-shaped geometry that I designed there, and the idea is to have less variability in the velocities. Instead of a cylinder, that we have a variability in velocities from 0 at the center to the maximum, and that's important, I think. Live imaging, we can see through the glass jacket, so we can take a look of this part. With 1 to 60 frames per second. Shear velocity is between 10 to the minus 5 to 10 meters per second, so we can get all of the range of the inertial numbers there. And in order to run it saturated, we're adding deionized water from the top. So, this is again the experimental setup. You see the acoustic sensors, the sand. Shearing is mostly localized here on the boundary. And what we control in this experiment is usually the constant applied normal stress. So the boundary condition is constant load, which means that the rotor can move up and down in order to preserve this boundary condition. The other thing we control is the rotor shear velocity. So we are saying to him what is the velocity he needs to move, and I will show you the procedure we have in the next slide. What we actually measure is dilation contraction, how this rotor is moving up and down because of the change of the stresses and other stuff. And I will call it gap here. It's marked by gap. Torque, how difficult it is to move to get this velocity, how to make this rotation. And not connected, independent measure is the acoustic emission at 2 megahertz. These 4 sensors. So that's a procedure of an experiment before when we plan the experiment and how it looks like actually during the experiment. This is the velocity, the angular velocity in radian per second. The other axis is the tangential velocities in meter per second, and this is the time along the experiment. So we accelerate from 0 to 1 millimeter per second, then jump to meter per second, and etc., etc. Each velocity step, constant velocity, is along 200 seconds. And according to calculation, the inertial number is 0.2 for the high velocity, which means that we should be in the inertial regime, and the low velocity is 2 × 10⁻⁴, which means that we should be in the quasi-static regime. So we're supposed to see it in our dilation measurements. And let's move to the dilation measurements. So indeed, we see the same pattern of the velocity in the results of the dilation compaction, the gap in microns here. So increasing the number here is dilation, more opening of the system, increasing volume. Down to lower numbers is decreasing the volume, compaction. And the observation we have, so first that's the time of the experiment, of course, dry experiments in red, water saturated in blue. And ever dilation is higher for dry. You see, if we can look even on the low velocity experiment and high velocity in general, we see a dilation pattern. While for the blue, for the wet experiment, we see even compaction. I will talk about this compaction. This may be explained by a little bit increasing pore pressure between the grains, and it's easier to them to slide and to find a better compaction in a wet system. The other thing is the general compaction, and I will touch it when I will show you some videos of the experiments. Longer time for the dry to reach a steady state. So here it's taking time until it's getting a steady state, maybe here. While for the wet, it's getting very fast to a steady state, and this is also maybe caused by a little bit change in pore pressure. And the last thing, which is the main thing I want to concentrate, is the delta gap. Is the change from low velocity to high velocity, back and forth, and that's like defining the delta gap because of the change of the physics of the system from quasi-static to the inertial regime. Let's take a look just about the delta gap, the absolute value of the delta gap versus the time of the experiments. So these are the jump between, each point is jump between low and high velocity. And what we see is that the dry is always higher than the saturated experiments, and it's about 3 times larger, the delta gap. So the question is why? Now let's try to see if we can get something from the experiments themselves, looking at the video. So this is a dry experiment, this is a water saturated experiment. I'm shearing the system at low velocities. It's slower, it's slow motion of the experiments, not a real time. And I think there is not a big difference between, this is a line that I put to show where is the base of the shearing grains. Personally, I don't think I see any big difference between the experiments. So this is for the low velocity. However, I want to say something else here that I don't know if you can see, but here on top, this is the water, and you can't really see the steel rotor behind, so it's a puck. What's going on is that the material that's crushed during the high velocity step is moving, is injected outside with the water to the upper parts, and then it's just deposited on the surface. And remember, if you remember the decrease, or the gradual decrease of the water saturated experiments, in the water saturated experiment, I think it's because of the injection of material and removal of particles of mass out of the system. The next is the high velocity step experiments. And again, there is a change, there is a slight change. You will see that's the low velocity particle, the particles is moving slower. They have thicker bend comparing to the water saturated. However, it's not a big difference. So I'm not sure if that's the reason for the difference of the delta gap. Okay. So maybe we can find the answer for the difference by their acoustic emission measurements. And the acoustic measurements looks like this. This is an amplitude in voltage versus the time of the experiment. And we see waveforms, and we can detect actually the first arrival in the red X here. And then we get the earthquake, the small earthquakes, and that is getting back to the noise level. The reason we are getting, and this is during a low velocity experiment, when we see the isolated, we can separate isolated events, and we can have different sources for events. We can get grain breakage, collapse of stress chains, frictional sliding between the grains, like sticks between two grains, or impacting between the grains, as we observed should be in the grain inertial regime. So these two are more supposed to appear because of things that are connected to the physics of low velocity of the quasi-static regime, while impacting grains is supposed to be connected to high inertial numbers and high velocities. So let's take a look at a low velocity experiment. Again, the 4 channels. Water saturated is blue, dry is red. And what can be easily seen is that the amplitude and the number of events is much higher for the water saturated experiment. And the question was if it's indeed a source, a different source mechanism, or something else. So looking carefully to it, we suggested that it's acoustic impedance. It's actually caused the difference, which means that less energy is moving between the granular flow to the glass jacket where we put our sensors, and therefore we are getting less acoustic energy there for the dry. However, if that's true, we need to look at all velocities, and in general see the same phenomenon at all the velocities. That's for dry, we always will have less acoustic energy. But when we are looking at the high velocity experiment, we see exactly the opposite. We are see that the power, the amplitude of the dry experiments is higher somehow. And what we think is it's that the grain impacts, the grains that are coming into an impacts that are actually dumped by the fluid, and therefore the collision is less energetic, and there we have less acoustic energy that's released. So this is a very noisy signals. In order to summarize it, we look at the acoustic power of this, which means the square of the amplitude of the waveforms, and this is the high velocity, this is the low velocity versus the time, and what we get is indeed for the high velocity dry experiments having more acoustic energy, comparing which is different from low velocity when they have less acoustic energy. So the explanation for it maybe, as I said, just from the drag force on each particle. And that can be, so the 2 particles are moving to each other, they have now a fluid, they have water there, so the viscosity is higher from the air, and therefore it's colliding with less velocity and less energy. However, that may be true, but if we are considering fluid dynamics, we need to consider random numbers. And if we are looking and putting the densities and the velocity and the size in the scale, which is the grain size, we are getting a number of 400, which is relatively high Reynolds number. Low Reynolds number is 10. Like something above 10 won't be not be relevant for this equation that is proportional to the viscosity. However, the drag force is also true, is proportional for the density in a different equation in a different way. And the change in density between air and water is much important. It's a 3 orders of magnitude different, and therefore the drag force is the same idea of reducing the velocity between the impacts can be the case also here. So what will be the case if we are going to use silicon oil when we're increasing the viscosity and the density is more or less is the same, there is not a big difference. Maybe we'll need to use a different equation for it. However, is it the same mechanism? So taking a different experiment, but the same idea as I showed before, gap, dilation, compaction versus the time, is the same velocity steps, dry, water saturated. and what will be the oil case. So my guess, it will be something like that. We'll get something even more damping because we're having a viscous material, viscous fluid. However, when we're looking at the results, we are getting the opposite. Okay, we are getting something with much higher dilation, even higher than the original dry material. However, there is still decrease in acoustic emission power, even more than in the water-saturated experiment. So the question how to explain this, and I think there is an exist theory about hydrodynamic lubrication. When the two particles are colliding in a viscous, especially when increasing to a viscous materials, the velocity of the fluid that's trying to move out, to squeeze out, is not fast enough, and therefore it's trapped there. The pressure increase in this part and actually having a repulsive force, applying a repulsive force on the two grains, on the grains there. So that may actually increase the dilation because the energy of these impacts is actually increased. They are moving more, and they are not losing energy in the impact itself. So to summarize it, we see that we have, I think, some insight about shearing in the presence of fluids. Dilation is higher for dry granular materials, at least in water. When we're talking in comparison with water, acoustic emission energy is lower for water-saturated granular materials, and high fluid viscosities tend to make the opposite, more dilation actually, but the acoustic energy is decreasing. So dilation and stress, we can add to this, I think, to this graph, the collisional damping that is causing, it's mainly controlled just pure water, and hydrodynamic lubrication effects if we're increasing the viscosity of the fluids. And this is relevant just for the high shear rates and the high inertial numbers. So to summarize, in general, shearing in the presence of water, what we learn. So in terms of glacial polish for glaciers and maybe to earthquakes and other detachment faults, a polish layer could form under low temperature pressure under wet shear conditions. And this is maybe different from what we saw previously about faults, that sintering and high temperatures control the formation of fault mirrors. The other thing is that mechanical and chemical processes are acting in concert to form this polish layer. We don't know exactly how it became from smeared mud to very hard surface, but it's probably this combination. For the debris flow and the shear zones in general, we conclude that acoustic emission and dilation are damped by the drag effects, I think, that's applied on the particles in between collisions. And acoustic emission is damped, but dilation increase because of hydrodynamic lubrication in more viscous fluids. These are two opposing mechanics in terms of the how the dilation or the stresses behave there, and its may play a critical role in saturated shear zones. So that's it. Thank you very much.
What is the dating that you use the polished mirror surface, the glacier polish, to date the glacier motion, right? So is there any other method to compare the new dating method of glacier motion? You got 34,000 years for the glacier motion. Did you compare it to another?
We compared it. Yeah, all the numbers that I gave, except of this 34,000, is cosmogenic isotopes of the exposure time of the bedrock in Yosemite.
I didn't understand. So they agree with this?
So the numbers in general agree. Yeah, with this specific day they can agree. Yeah.
So you have a new dating method for glacier?
We hope that we have a new one. That's the idea. Trying to have a new method that give you something different from, again, the benefit, I think, is instead of looking on the erosion and what is removed and exposed, but what's removed, we're having a sedimentary layer we can date, and it's in situ. That's the benefit, I think. And also the interesting part there is that you can compare between different methods. So one is cosmogenic isotopes. Now there is a different in situ OSL method. It's used in the outstream OSL, optical stimulated luminescence, that they are using. But instead of looking at a decay of 2 meters in cosmogenic isotopes, they are looking a few millimeters from the surface, and they can date when it was exposed. So we have something of microns, and we want to compare between, and maybe it will tell us about erosion rates and different processes in the base of glaciers. So that's the way we are taking it, but first we are trying to understand if we really have here a new method. So we can apply the no method on a new layer.
Okay. And what is it? And regarding the second part of your talk, when you have the what is the implication that you have different dilation in the water than the dry granular material? What is the implication that you can say about the motion or friction or?
So it's a good question. We measure friction, but I think it will be more relevant when we apply different boundary conditions. We'll apply the constant volume boundary condition, and then it may be reflected by the friction. How it will reflect by the friction, I'm not sure. But I think it's maybe changing volume if it's trapped for it. I think that's what.
So it's the fact that you have the elevated core pressure.
That I have?
That you have elevated core pressure that might reduce the friction.
I'm not sure. Because in general, what we are trying to say here is that, and one of the reasons I decided to make this monosaturated experiments is because we are applying a very small amount of force in our system. It's a few centimeters, 10 centimeters of sediment. That's the equivalent to the stress, which is tiny. However, I think water, maybe in high pore pressure in general in nature, so the effective pressure is maybe similar to what we are doing in our lab. And therefore, I think the mechanism that I talked about hydrodynamic lubrication and the drag force that is applying, dumping on the grains, is not connected directly to the pore pressure itself. So the pore pressure can be high, can be low, but it will act because of this differential mechanism.
Any more questions? Thank you.
הזמן, דבר לי.
איפה אתה יושב? אז כלומר, אתה אומרת שיהיה ירבול בין הגיל המקורי של הסצנה? שאלתי אותה שאלה ולא קיבלתי תשובה. אני לא רואה לו, אני שם כאילו בואו נעזור להשקיע לי, רוצה לתוצאות של